Assalamu alaikum students. Welcome to our new lecture on hydrology and water resources management of your BSc Civil Engineering course. We are almost reaching the end of our course contents. In the last lecture we looked into introduction to floods and its causes. We looked into frequency calculations of different kinds of return periods, different kinds of plotting positions, and I also shared with you some Excel sheet where all the calculations were done. We are now doing the last part of that lecture, which is related with flood control structures and introduction to hydrological modeling. And after that, we are only left with one lecture, which is related with the groundwater that we would be doing next week, inshallah. So today we are going to talk about flood control structures and hydrological modeling. References are the same. Certain books are shared with you, and also I am sharing with you these slides and also certain chapters of the book that I find interesting or I find important for you to go through. We started with introduction to floods and its causes and the frequency and duration analysis. We also looked into the routing problem and we solved in detail one numerical on routing. Today we are going to start with flood control structures followed by the introduction to hydrological modeling. So let's start with different kind of structures that are usually provided along the river for flood control. Before we go to those structures, it is important to understand the behavior of floods. We briefly talked about different kinds of processes that are important for the flood estimates, and we also looked into the factors which would be affecting the floods. But let's go through certain things which should be kept in mind when designing for the flood control structures. First of them is the stream order. You can see here that we have a certain catchment and we have a river which is flowing in this direction, and then there are certain streams which are meeting this main river and draining its water into this main river, which is ultimately going out of this catchment area. Now this, for example, stream order is important to look into because if you are somewhere here in this area, then the design that you are going to do for flood control structures should be different than the designs that you are going to employ in this area. And it is understandable because this is the area which is kind of head catchment, and the discharge here would be less as compared to discharge here, because here we see that all the streams are ultimately combining here. So it's important to look or to understand which stream I'm working on. Am I expected to make a flood control structure here, or is the flood control structure going to be made here? So you also see here the hydrograph for the stream order, which is somewhere here. If we are in stream order 1, then your hydrograph would more or less look like this. If you are somewhere here downstream where you are just getting out of the catchment area, then your hydrograph would look like this. So you have a larger amount of water to deal with if you are dealing somewhere at the 4 stream order. But if it is just the first stream order, then obviously the discharge is less, and that's why the flood related control structure that you are going to design would be smaller. So it's important to look at the stream order when you are looking into the designing. Region climate is important. We already talked about it, and we said that different kinds of climate would create different kinds of floods, even if the precipitation amount is the same. Yeah, this is understandable. So you also need to take care in which area, in which kind of climate you are designing a flood control structures. Geological features of the area are important to look into. If you are in area where it is mostly shale, the hydrograph should be expected, which is has a very quick and abrupt rise and very quick and abrupt fall. So very kind of less time for you to react to the flood event. So the discharge or the control structure that you are going to provide should be able to keep this thing into consideration. If it's a limestone, then the increase would be quicker, but the release would be very slow, and that's why the control structure that you are going to employ should keep this thing in mind, and it should be such that it can store water for a longer period of time, as opposed to a structure which is a geological substrate which is mostly shale. So another important feature to look into. This is the geometry structure and its effect on the hydrograph. We looked into it in the, I think, 2 or 3 weeks ago. If you have a geometry which is mostly elongated, then obviously it will take some time for the water which has fallen here as precipitation to change into flood and then reach all the way down to this point. So it will need more time to reach here, and that's why your hydrograph would be increasing slowly, and then it would remain in the catchment for a very long time until this hydrograph reached back to its base flow period, as opposed to a basin geometry which is more or less like this. Here you see that the distance that the water has to is to go through until it reached the exit point of the catchment is not that much, so that distance is not that much. So you see that the hydrograph is going up very quickly, and then it's also going down rather quickly. So you need to keep these things in mind. Land use is important, of course. More urban area you have, the more discharge it would be created, and therefore if you are asked to design a flood control structure in this area, then obviously you have to keep this in mind, that the water would be reaching the control structure very quickly. A kind of reservoir, whatever you are designing, should be able to accommodate that water. And then important consideration is the return period of the flood. Are you working on a 50-year return period, working on a 25-year return period, or a 100-year return period of flood? A 100-year flood is basically a flood that has 1% probability of occurring in any given year. So this is just a occurrence probability, a 1% probability of occurrence. But keep in mind that the percentage is 1%, but it can be, it doesn't mean that a 100-year flood would occur only once in a 100 year. Its probability is 1%, but obviously that 1% can mean 2 or 3 events in a year. But 100-year flood event is basically an event which has 1% probability, and there would be a certain discharge amount which would be related to it. So we would be associating a flood, or let's say discharge amount, with a 100-year flood event, and we will be designing for that thing. We also looked into this example. So let's say we are calculating the return period here. Let's say you have a certain record of discharge data available to you. For example, let's say from 1905 to maybe 2000 or 2005, and you have the the annual maximum flows available to you. So in which year, for each year, you have the maximum amount of discharge available to you. We plot all the data in a simple graph, and we see how many times a certain threshold is exceeded. So for example, let's say I'm looking at the threshold of 200,000 cubic feet per second. So I'll see, for example, this red line is that threshold value. Sorry, this is not showing it correctly. This red line should be here against 200 200,000 cubic feet per second. So we will look at our threshold, and if our threshold is, let's say, 200,000 cubic feet per second, we'll try to count the number of times that this threshold is exceeded. So we'll see that, okay, this 200,000 cubic feet per second is exceeded 1, 2, 3 times. The number of occurrences in a 106-year period is 3, which means that the recurrence interval is 2, because you see between this you have one recurrence between the first two events, and then you between second and third there is the third occurrence. So you have 2 recurrence intervals. We simply divide this 106, the total number of available years, divided by the recurrence interval, and you get the return period of that particular threshold. So 200,000 cubic feet per second has a return period of 53 years, which means that after every 53 years this flood will occur. Now if I reduce my threshold value, let's say to half, to 100,000 cubic feet per second, so this blue line should be here, should be drawn here. I'll give you the correct graph when I'm sending it to you, but anyways, so you put your threshold line here, and then you count the number of times that this threshold is exceeded. 1, 2, 3, 4, 5, 6, 7, 8 times this threshold is exceeded. The recurrence intervals in 106 year is number of occurrences minus 1, so 7, and then 106 divided by 7 will give you the recurrence interval for 100,000 cubic feet per second, which is 15 years. So this value would be occurring every 15 years, this value every 53 years. So you see, it's not simply that if you are doubling your threshold from 100,000 to, let's say, 200,000, then you should simply say that because for 100,000 cubic feet per second my return period is 15 years, so for 200,000 cubic feet per second it should be 30 years. It doesn't work like that. You have to calculate all those things and see what the return period is. So basically we calculate the return periods, and based on that we try to design our control structure. Usually we have the storage reservoir control. We design a reservoir, and that reservoir has a particular zone in which we are controlling the flood, or you provide flood detention, different flood detention structure. If you are looking at the reservoir control, then I guess we looked into the reservoirs in the previous lectures, and we said that different reservoirs may have different kinds of uses, and those uses can be conflicting uses. For example, let's say you have a reservoir which is also providing water for irrigation, for power supply, for recreation purposes, and at the same time this reservoir is also catering for the flood. Then these are conflicting goals. For maximum hydropower you need to have maximum water level. For flood control you have to have your water level minimum so that maximum flood can be stored, but obviously this is another topic, optimization of use of reservoir. But anyways, so we have reservoirs, and these reservoirs can have multi-purpose functions, and we need to use our reservoir in such a way that all the uses or all the goals, purposes are met. We also need to understand that for a reservoir is not catering for the flood control or not working as a flood control structure throughout the year. We have a flood season, and particular in that season we have to make sure that we have maximum space available in our reservoir so that the flood water can be saved, can be stored, and that later on we can release that flood water when the peak is gone, so that the downstream destruction or the downstream effects are minimum. So usually we, if this is, let's say, our reservoir, then we have different kinds of levels which we identify for different kind of purposes, and each zone or each space is used for its own purpose. And these purposes are usually defined through the operation rules, reservoir operation rules. These are the rules which are developed based on the reservoir function for the last 50-100 years, with the experience of the reservoir managers or decision makers. They usually develop these operation rules, and then these operation rules, they are usually modified in the initial 20-30 years. And once you have a fixed knowledge of all the different kinds of flooding seasons and different kinds of situation in your catchment area, then more or less your reservoir operation rules becomes fixed, and the people who are sitting there and managing the reservoir, they take decision based on those rules. You have to keep in mind the hydrological conditions, the water demands, and the time of year when you are taking the decision to operate a reservoir. And usually we have an operation rule which is something like this. For different months you have different kinds of zones, and you need to make sure that your zone 5, for example, is in March somewhere between 150-155 meter. In the flooding season, for example, this zone can be reduced so that you have maximum space available for the flood season. So you see, we classify our reservoir into different zones, and then those zones, each of the zone has its own operation rule with respect to the time of the year, and we follow these operation rules so that the reservoir can be taken maximum advantage of. So flood detention, that was the reservoir. Another structures that we usually provide are the flood detention structures. These are the structures which store the flood water on a temporary basis, so that the downstream water levels are reduced. They are usually dry in normal situation, but once there is a flooding season, we divert water to these detention areas, and the water is stored during the rising limb. And once we know that now the precipitation has ceased and now it's a falling limb period, then the water is released into the river. The main objective is basically to reduce the flood peak. You see, a flood peak, or let's say the peak of the hydrograph, would be reduced by these kinds of flood detention structures. These detention basins can be adjacent to the river, or they can be in line with the river, and we'll see certain examples. For example, let's say we are the detention basins which are adjacent to the river are basically structures that take certain amount of water from the river. It store it for a certain period of time, and then we release it back to the river after some time when the hydrograph has subsided. For example, let's say this is your hydrograph, increasing hydrograph, and once we sense that okay, now the discharge is increasing above certain level, then we start taking water out, and that volume of water is stored in the detention basins which are adjacent to the river. And once the flood peak, or let's say the hydrograph, start falling down, we start releasing water at a later time period. This is one example of that. For example, let's say this is your river which is flowing in this direction. This is an example of detention basin from Elbe River in Germany. And then you have these areas adjacent to the river which are controlled by these control structures. These are gates or levees or weirs which are operated once the water start increasing, and then we store water in this area. If the flood is too much, then we even divert water to the lower or to the other area through another control structure, and water is stored in this area. Once we see that now this the flood is subsiding, then we start releasing water into the river through other control structures which are shown here. This is another example where you are diverting water to a certain area and then releasing it back to the river so that the locality is saved from the high discharge volume. The hydrograph would obviously be reduced something like this. Then we have inline river structures. They usually are used when the river capacity is exceeded by the incoming water, and we divert water to these areas which are very adjacent, or let's say they are in line with the river. These are the areas which can be even within the river boundaries, but because you see we have these meandering kind of structures in the river, so these are basically part of the river, but they are not usually flooded, or the water is not going to those areas, and then once the water increases, then we divert water to it, or provide structure so that the water can be diverted to them. This is one example of this structure. In a normal situation, the flood basin would be working like this, but once when we have a flood, you see that these gates are opened up and the water is released into the adjacent areas. Some other examples here of the detention basin along the river structures. Next in our course content is Introduction to Hydrological Modelling. A very important, very interesting part of hydrology is hydrological modeling, which is used for planning purposes, for management purposes, and also for the climate change studies. The goal is that we try to mimic the behavior of river through mathematical or statistical model. So basically we are trying to simulate the shape of the hydrograph by observing the natural hydrograph and then developing formulas, developing mathematical equation in such a way that if we give a certain precipitation amount or certain input value, then our model can tell us what would be the discharge value associated with it. So basically, let's say you have for a certain time you have precipitation amount. We know that this precipitation amount, once it falls on a catchment, it will take some time for this precipitation to take a shape of river discharge and then to show up in river as a hydrograph. So we do the same thing. We just take this precipitation amount and we do certain calculation with it. We play around with the precipitation values and with a lot of different other values of temperature and humidity and evapotranspiration, a lot of other things, and we do certain, let's say, a kind of magic with it through mathematical equations, and we try to develop the hydrograph. Now, how these mathematical equations are developed, how this modeling is done, is not part, or let's say it's not the scope of this undergrad study. Usually we teach these advanced topics in the MS of Water Resources Engineering and Management, but you have studied almost all the basics associated with it. You see, you have studied the unit hydrograph, you have studied the way precipitation, evapotranspiration, discharge, and other values or other variables, how they change with respect to time, and how they behave over the years. If you have all those information available to you, so your basics are already made, then the question is to combine all those things into one, let's say put all the things in one basket, and relate them with each other and try to develop an equation. That is basically the whole story of hydrological model. Model basically, or what we can use it for is, first of all, for a future design event. You see, once you have a developed hydrological model, and you know that for, let's say, for 20 millimeters of precipitation, your catchment is producing, let's say, 100 cubic meters of water per second, then you can manage the things in future, and you can say that, okay, for 20 it is reacting like this, then how my catchment would be reacting for, let's say, 40 millimeters of precipitation. So you try to forecast what would happen if your precipitation value changes. The model also can be used for the past situation. You see, in the past, maybe in 1960s or in 1940s or in 1930s, Indus River faced a certain flood. We didn't had all those sophisticated kind of techniques available to us at that time, and we want to study the past events, what was the precipitation in that period, how that precipitation converted into the flood, and what was the time it took for the precipitation to change into the flood, and all those kind of studies. So once a model is developed, it can also be used for the past time. And basically we are trying to relate different kind of things to create discharge. So for example, your model would be a function of precipitation, your model would be a function of landscape properties, of what the climate conditions are, of what the geological conditions are, and then we put all those things together and we convert them into a discharge. So kind of you have a kind of a bucket of equations that you put in all the equations there, and you convert this thing into this thing. Now there are different types of models. There would be physical models, and then there were analog and mathematical models. Depending upon how much data is available to you, and depending upon in which kind of area you are, you would be developing different kinds of model. We'll see what physical models are and what are the pros and cons of each one of the model. So first of all, let's say look at the physically based models. Physically based models are basically those models which try to mimic the actual physics of the process in the catchment. So what we mean the actual physics or actual occurrence of things is that how water is falling on the surface, how that precipitation is then infiltrating into the soil, what part of that is infiltrated into the soil, what part of the precipitation is going on the surface, and we do all those things with detailed physical manifestations. We do this with all the physical details available to us. All the energy balance equations, the snow melt equations, and all those equations are used there. So understandably, if you are using a physically based model, you have to have a lot of data available to you. This is one thing that should be kept in mind. Another models are then the conceptual model. These are basically the models which kind of simplify the processes. It is not going into the detail of how the water is infiltrating into the ground and how it is changing its properties when moving in the soil. and going into the, let's say, confined aquifer and unconfined aquifer. It doesn't deal with all those things. We try to simplify things in conceptual model. We try to relate it based on probability, based on historic time series. You take decision, you calculate probabilities, and you assume that, okay, if the things have worked in such a way in the past period, then our assumption is that it would work in the same way in the future, which obviously is not a very good assumption, but this is the assumption that is inherent in when you are working with a time series, or let's say when we are evaluating along would be represented with stochastic processes. Certain processes would be represented by using empirical or regression equations, and certain processes would be represented by the physically based equations. Then there is also the spatial representation thing, which means that how you are combining things in your catchment, whether your catchment, you are representing your catchment as a lumped catchment or as a distributed catchment. By lumped representation, we mean that we are assuming that most of the things in the whole catchments are the same. For example, your infiltration or your porosity, or let's say your evaporation, is more or less the same in over the whole catchment area. So you are kind of defining your catchment as one similar kind of homogeneous structure, and everything that is happening in one part of the catchment is occurring in the same way in another part of the catchment. So that would be lumping everything together. Distributed models, or let's say distributed representation of a catchment, is such where you excuse me, where you divide your whole catchment into different parts, and you say that one part is acting in one manner and another part is acting in another manner. So you are kind of tailoring each and every part of your catchment differently, which obviously makes sense because some parts of your catchment would be urban areas, so that should react differently than the area which is agriculture area. So that would be then your distributed representation of a catchment. Conceptual rainfall runoff model are the most commonly used type of hydrological model. We simplify things, as I said earlier, into different boxes, and we said that, okay, these are the processes which are occurring in this way, and then we combine things together and try to mimic the physical process of hydrology. Distributed or physically based model, as I said earlier, are the models which attempt to model each and every process individually. You would have a finite different kind of representation in your catchment, and then you'll try to derive empirical equations and put all the things together, and for each and every process you would be having different kind of formulation. For evapotranspiration, for example, let's say you are using the Penman method, and then for, let's say, for unsaturated flow you are using the Richards equation or the Darcy-Lie equation. So every process would be defined as it is required, and then for each part of the catchment you will be calculating each and everything. So if you have a catchment, then you will start from the very top, or let's say from the head catchment area, you'll start calculating things. You will process those results to the lower areas, then you will do all the calculations again. You will process those results to the lower areas until and unless when you reach to the final point where your water is going out of your catchment. As I said earlier, these models are very data hungry, and by data hungry we mean that they require a lot of data. So for each and every location, let's say, what is the porosity, what is the area like, what is the precipitation there, what is the temperature there. So a lot of data would be required, and if that data is not let's say on the ground station based available, then we'll try to provide their data from the remotely sensed data, which means radars or satellites and those kind of things. So a physically based model, a distributed physically based model would be having its advantages and disadvantages. Let's say this is one of your catchment, and as I said, we'll divide each and every part of the catchment in quite detail, and then a finite difference method would be used or other methods would be used, and you'll start calculating values at each grid point or at each node of this grid. You will transfer those values to the next grid, until you reach to the river, and then you do all the calculation in the river, and you finally, when you drain all the water out of this thing, you keep in consideration the topography of area, you keep in consideration the exposure of each grid to the sunlight. So the point is that quite elaborate data structure is required. The pros, or let's say the advantages of the physically based model, are that you get fairly accurate results. These are physically based equations, they are based on the physical processes, so you mathematically you are sound, you are quite sure about the things that you are doing. The results, I wouldn't say that the results are also very accurate, but at least you are sure about the processes that you are doing inside your model. The disadvantages obviously are that you require a lot of data, and once you have a lot of data, you need a lot of computation power with you so that you can do all those calculations. You see, you are not going to develop a model for one day or for 1 month or for 1 week. You are going to develop your model based on 100 years of data, and once that model is developed, it has to calculate different kind of things. It has to convert precipitation into discharge, and then it has to keep in mind the evapotranspiration, the humidity, the temperatures, each and everything, the snow melts. So it take a lot of computation powers to calculate each and every value at different kind at all the grid points. The main purpose, or let's say the very first purpose usually, or the very first step that we usually do, is the precipitation, the fall in precipitation. There would be losses, and by losses we mean that part of precipitation which has gone down into the surface, and then there would be another part which is called effective precipitation, that if precipitation which is actually going on or it is the direct discharge, which is called the direct discharge, or that part of precipitation which is flowing on the surface, ultimately reaching the river surface, and that is that precipitation that we are interested in. We usually divide let's say this is our total precipitation. We kind of employ different techniques. We have already worked with SCS method. One method was SCS that you have already looked into, where we designate certain part of precipitation as losses and certain part of precipitation to be the direct precipitation. Then that precipitation is then converted into discharge. So main goal of the model is to mimic the natural process of a catchment, and this is usually the graph, or let's say this is the data, the picture that you ultimately would be looking at. That what was your observed discharge, so this black line is basically your observed value, and once you applied all the things, all the data to your model, and your model gave you the results, then the blue line is the one which is the simulated discharge. And our goal is that these two lines are as close to each other as possible. You see, in this area our model is not performing well because the observed value was higher and our simulated value is lower. And then there are certain areas where your model is overestimating the value, the observed value. So your observed discharge was something like this, but your model is telling you that the value is something like this. So our goal is that these two lines are as close to each other. And of course this wouldn't be happening unless and until you also model the processes uh, in the same way. So for example, let's say you model the snow depth. Your model is predicting or forecasting or giving you the proper values of the snow depth in the catchment. Your model is also giving you good results on the temperature and also giving you good results on the precipitation. So again, you see the blue line is the measured temperature and red is the model temperature, and the same here for precipitation. So if these smaller processes are occurring in a correct manner, then ultimately this thing would also be quite good. But if your underlying processes are wrong, for example, here we see that the snow depth is not modeled very accurately, then obviously it would be having an effect on the discharge at the end of the modeling process. So this is basically the whole process of modeling. Calibration and validation usually is a process which is usually performed in the model. We need to evaluate our model. You see, when you are looking at this graph, one of your friend would be telling you that this model is very good based on looking or let's say by just looking at this graph. Another friend of yours, or let's say another guy, when he's looking at this graph, he would be telling you that the model is not very good, it's not working very nice, because you see here at this point the model is behaving very badly. You see, so everybody would be having his own opinion about this graph. But in the calibration and validation purposes, we try to evaluate the model performance by using different equations, by using different objective functions, so that ultimately we can have an objective assessment of our model. Calibration is basically more or less the same thing, where we try, it's not entirely that thing, but calibration is basically when you are trying to train your model to do the job. How we do it is would be explained now. First of all, you need to look at the accuracy, how accurate your model is. What is the degree of accuracy? What is the degree of precision in your model? So your model can be consistent. I mean, it will be giving you, for example, for every 20 mm of precipitation, it is always giving you 100 cubic meters per second of discharge. So it's very precise, it is doing everything very correctly. But is this 100 cubic meters per second of water close to reality? Although your model is always behaving in the same way, but is this 100 value a correct value? So we need to evaluate our model performance using different kind of metrics. We look at the precision, we look at the correspondence, for example, how the values are corresponding to each other. And this calibration process is usually a long process where you try to train your model and you look at the two values of observed and simulated values, and then you use it for validation purposes. Now, there are always uncertainties in the model. You would be having, for example, the values that you are recording at the catchment, precipitation value, for example. Your instrument would be recording a certain millimeter of precipitation, but is this millimeter of precipitation the real value of precipitation? So you have certain uncertainties associated with the way you are collecting the data. whether it's temperature, precipitation, and whatever. Those uncertainties are ultimately translated into your modeling process and ultimately your output that you are looking at. What we do in calibration is that we try to, as I said earlier, we are training our model. We are training our model to give us good results. And this training is done by changing the parameters of different parameters of the model. For example, let's say precipitation. Precipitation, a certain value, or let's say certain millimeters of precipitation is falling. Some part of it will go to the ground, some part of it will be on the surface. Now, what part is going into the surface? Usually these are calculated using the equation, the SCS method. If you remember, we looked into this SCS method used a curve number method. Now this curve number is you can think of it as a parameter. There are other parameters as well which are usually used in the equation. So these are the parameters that you would try to change. For example, let's say another thing would be how you use the field capacity. How do you use the soil moisture in your model? Now, with increase in precipitation, the soil moisture would be increasing. If you have higher soil moisture, it would mean that less water is going into the surface and more water is going over the surface, right? So we are trying to connect discharge with the soil moisture as well, and this equation would be having certain parameters. So these parameters are usually fixed, or let's say they are changed until we reach to a point where we say that my model is now working fine. So it's a tweaking process. You are changing one thing, looking at the result. You are changing another thing, looking at the results. And once that process is complete, you will say that my model is calibrated. And these variables which are usually evaluated or calibrated are the parameters which are associated with the water balance equations, and as I said earlier, with the soil moisture equation and different other processes. So each and every process would be having its parameter, and those parameters would be tweaked. We look at different kinds of objective functions, and by objective function we mean we are ultimately calculating how my model is performing. These performance indicators are biases, the mean square error, the root mean square error, the coefficient of determination, the Nash-Sutcliffe efficiency. These are the things you should know about at this stage, at this undergrad stage. You should know that there are certain objective functions that we have to use to find out how my model is performing. The details of it are not relevant here, and that's why I'm not going into the bias equation or the mean square root equation and how those equations are developed and what really these equation means. For example, mean square root error is an equation which basically tells you how much you are away from the average response of your model from the observed value, these kind of things. These are the equations, but you should look into it, but it's not important to understand them at this time. Calibration can be done manually or automatically. By automatic method we mean this calibration is done in a way where we calculate different equations, different objective functions. For example, these values, these matrices, the coefficient of determination, the Nash-Sutcliffe efficiency parameters, these are calculated, and then we see, okay, what is the things that I have to change so that this value is improved, and the model automatically do all these things. This is an automatic calibration. Manual calibration is where you try to change certain values yourself, certain parameter values within certain range. You change them and then you look at the result. But manual calibration is a highly labor intensive. I mean, it takes a lot of time that your model is calibrated, and you can use it for the future studies. It takes time. It's difficult to learn in a sense that you have to understand how each parameter is affecting your ultimately the discharge. You see how in each equation what is the role of that particular parameter. By changing it, what are you basically changing? For example, if you are changing one parameter which is just changing the peak of the flow, then it would be affecting, it might be good for the flood situation, but in a low flow situation your model would then be not working very fine. So you have to find a parameter, or you have to adjust your parameter in such a way that your model is working in a proper way both in flood situation and also in the low flow situation. So it is you see it takes time to learn which parameter is affecting the model in which way. Okay, these are things that you should look into yourself, and ultimately we come across these kind of things. HBV light is one model which is extensively used in different areas. It's a conceptual rainfall runoff model, and ultimately we kind of, you see the observed values are in blue and the simulated, or let's say the model values, are in the red. This lower panel shows you the discharge, and it also gives you all those values. What is the root mean square error, what is the coefficient of determination, the Nash-Sutcliffe flow efficiency, what is the bias, and based on that you can then change different other things using these things here. This is a GUI of a model, but usually the hydrologists prefer to work on a language, or let's say in a Fortran developed program where they can change each parameter easily, and then they can look at the results. GUIs are also very good, but then sometimes you lose the reality of how the model is working. So these are different examples. I've also put references here. You should look into them. All the references are here. I'll also be uploading certain papers so you can look into them. So for example, let's say this is one example from this reference where different kinds of parameters, or let's say the variables, are ultimately computed. What is the snow depth, the modeled and observed snow depth? What is the evaporation? What are the root mean square error? What are the groundwater levels? And ultimately the discharge value. So you see each panel is showing you the performance of the model with regards to different physical processes: evaporation, water levels, the nitrogen values or the phosphorus values in the stream, and the discharge values, and you can see how the model is performing. Validation is basically once your model is calibrated, you then apply that model for another time period. So let's say if you have data available to you from 1930 to 1950, then the first 10 years you are the first 10-year data you are using just for calibration purposes. You are tweaking your model, you are changing certain things, and once you are confident that now your model is okay, then you start validating your model in a way that the data from 1940 to 1950 is applied on the model, and then you look at the result, whether the result is more or less the same as in the calibration period, or let's say the performance is the same as it was in the calibration period, or whether it has improved or it has deteriorated. So validation process is that process where you put independent data set on your model and you try to assess how your model is working. So for example, I showed you this graph where your R square value was 0.91 and your Nash-Sutcliffe efficiency coefficient was 0.91. So both the matrix or both the objective functions are 0.91 in the calibration period. When we look at the validation period, then the same has reduced to 0.81 and 0.67. And this is usually the case, not always, but it is usually the case that in calibration your parameters, or let's say your objective functions, are working very nice, but once you apply, or let's say once you validate your model, your performance kind of start decreasing. It shouldn't decrease too much. For example, still when you look at the time series, you still would observe that your model is performing quite nicely, but these numbers are showing you the real performance of your model. This is still a very valid, or let's say acceptable performance of a model. In validation, the coefficient determination of 0.81 and the Nash-Sutcliffe efficiency coefficient of 0.67, it is still very good. But anyways, calibration was the process of modeling where you put a data to the model, you start processing your model by changing parameters, and you reach a conclusion that now your model is working fine. Validation is that process when now that you have found out your parameter values, you have fixed your parameters in the calibration, and without changing the parameters, now you are just changing the data and you're looking at the results. So in a calibration process, you fix your parameters in such a way that you are satisfied with the model results. Once you are satisfied your model results, you fix those parameters, you are not changing them again, but you just change the data, and by data I mean the precipitation values, the temperature values, and these kind of things. The parameters remains the same as you have fixed them in calibration, and you then run your model and you see how your model is performing. So that was basically about calibration and validation processes. So that's it for today. For hydrological introduction to hydrological model, this is I think enough at this level that you have at least an idea of what the hydrological models are and what are different kind of terminologies, the validation, the calibration, the model performance, the biases, the parameters, and let's say the calibration time period and the validation time period. You should know about these things once you are going into the higher studies, into the MS level or PhD level, then you would be applying them in real sense. So till then, until next week, I thank you and Allah Hafiz.